All right, the topic of entropy is really important in determining whether a reaction is going to run or not, and that's pretty much what this chapter is all about. When we get into free energy, this involves entropy. But more importantly, entropy is kind of a phenomenon that people don't really understand, but if they think about it, it makes total sense. Entropy is a fancy word for disorder or chaos. And basically the second law of thermodynamics states that as time progresses, particularly whether it's a chemical reaction or just life in general, things tend to get more disordered, more chaotic. Just look at the human body and how it functions once it gets past its peak at the age of 27. Delta S, when we put a Greek letter capital delta, that means it's a change in entropy, and that allows us to get negative values. And what I mean by that is this. Delta S is positive for increased disorder, and if the change is going towards more order, then it's going to be negative. So an example of positive delta S happening is when you're going from a solid to a liquid or liquid to a gas. It is a natural situation. Reactions that tend to take place are those that you would expect to take place without any help or not very much help. A negative delta S, it sounds like it's better because it's more order, but since nature prefers disorder, then this is going to be negative values. And this is a case where if you're taking a gas or a liquid and then changing it down to solid. Solids are extremely organized, gases are completely random, and liquid is somewhere in between. Okay? Now, so how do we measure that mathematically? Well, here's the thing about that. Let's take an example here. We have liquid ethanol, which we talked about in Chem 2. It's a 2-carbon alcohol. Has an entropy of 161 joules per mole Kelvin. Now that doesn't mean a whole lot to us, but the fact that it's positive means it is pretty disordered. If the heat of vaporization, meaning going from liquid ethanol to gaseous ethanol, is 25 degrees Celsius, that is going to be 42.3 kilojoules per mole. What is the total entropy at 12.5 grams of vapor? Now, the heat of vaporization here is an endothermic reaction, so that's kind of unnatural. And so we've got a natural situation with an increase in disorder, and then you got kind of an unnatural endothermic reaction that is taking place. So you got kind of a tug of war between the two aspects of this. So how do we calculate this? Well, first of all, the formula for finding delta S, if you don't have that given to you, and in one situation here we do. Now what's happening in this is that we are given the entropy in the problem of the vapor itself. So we're measuring the amount of entropy that causes this change, and then we're going to add that or figure out how many 12.5 grams, how much entropy is being involved in that. We'll get into that in just a little bit. But we're going to add that to the entropy that we have for 161 joules per mole Kelvin, again taking into effect that we have 12.5 grams of the vapor, as you'll see here. So how much total entropy is involved here? Well, first of all, since the general formula for entropy, if it's not given to you, is Q over T. Q, by the way, is heat, or enthalpy, or delta H, however you want to call it. We're given here that it's 42.3 kilojoules per mole. We need to change that over to joules because entropy is measured in joules per mole Kelvin, or just plain joules per Kelvin. So, and we have to change our temperature over to Kelvin. So the 25 degrees Celsius that we're given in the problem has to be changed over to Kelvin, which would be 298. You divide that out, you get 142 joules per Kelvin mole. But we had to figure out how many moles we had of this stuff, which, oh yeah, here it is. 12.5 grams, it has to be changed to moles, and ethanol CH3CH2OH is 46.0 grams, or 46.1, depending on how you want to round off hydrogen. And I got 0.271 moles for that. That is the quantity we're going to multiply by to get joules per Kelvin. So I take the answer I got here and multiply by 0.271 moles, and I get for that quantity 38.5 joules per Kelvin. Then since I have two things going on here, I have to look at the delta S for the liquid ethanol itself. And we already were told that it is 161 joules per mole Kelvin, but we only have 0.271 moles. The moles cancel out, and that gives us 43.6 joules per Kelvin. Add those two together, and we get 82.1 joules per Kelvin is our total entropy value. Now, again, that number doesn't mean a lot to you right now. It will later on when we get into the Gibbs free energy. Now, here's an example that's a little simpler where they just want to find out what the entropy is. So we're just looking at the phase change from liquid to gas. It's a positive value because it's endothermic, it's absorbing heat. So delta S is Q over T. The fact that you are going to create more gas or lots of gas from liquid, which is going from an semi-ordered to a completely disordered system, should give us a positive value. And this is going to be 29,600 joules per mole is what we get when we change the kilojoules per mole to joules per mole. Divided by the boiling point, which is 61 degrees Celsius. I probably should put that up there. The boiling point of chloroform is 61 degrees Celsius. That's in the problem on page 833. And you change that to Kelvin by adding 273, divide that out, and it gives you 88.6 joules per mole Kelvin. We are told that we have 1.20 moles of the stuff, so the total entropy in this system is that 1.20 moles times that value just found. The moles cancel out, and that gives us 106 joules per Kelvin. Okay, we have 3 problems to do, or practice problems that are similar to these. Have fun.